Now let's introduce our spotlight paper at ICML 2024, which uses end-to-end neural symbolic reinforcement learning to obtain high-performance policies and uses large language models to generate explanations that are understandable to people who are not domain experts. Our method is based on the improvement of neural symbolic reinforcement learning. As we all know, the current deep reinforcement learning is based on neural networks, which makes it uninterpretable. This problem can be alleviated by introducing interpretable symbols, which is called neuro-symbolic reinforcement learning. The first drawback of this approach is that it requires domain experts to explain, because symbolic policy cannot be directly understood by people. So one of our contributions is to use a large language model to explain symbolic policy, without assuming that the user is a domain expert. The second drawback of this method is that it cannot be trained end-to-end. Previous methods either fixed the encoder or used gradient-free methods such as genetic algorithms to optimize the symbolic policy, which resulted in the encoder being unable to gain gains through backpropagation gradients. So our second contribution is a differentiable CNN and equation learner that optimizes the encoder using reward information through end-to-end training. Our method, named Insight, takes a frame as input and generates a segmentation of that frame, and outputs coordinates as symbolic representations. Insight combines these symbols and generates a symbolic policy. Afterwards, Insight will give a policy interpretation, which is a general explanation of the symbolic policy. Then, Insight will give a decision explanation, which is an explanation of why the policy performs a certain action in a specific state. Next, let me briefly introduce how Insight works. First, the algorithm interacts with the environment and is trained through end-to-end reinforcement learning, using reward information to optimize the visual perception module and learn symbolic policy at the same time. The learned symbolic strategies are then used through LLM to generate explanations that can be understood by people without domain background. In the visual perception section, we used a 3-layer lightweight CNN to distill the large segmentation tracking model SAMTrack and achieved millisecond-level inference speed. The coordinates and presence information extracted by the CNN are fed into a differentiable equation learning network. We creatively use a neural actor to interact with the environment and use symbolic actors to mimic the neural actor, achieving results comparable to the neural baseline. The symbolic policy learned by reinforcement learning training is input into LLM, which generates 2 types of illustrations. The first is policy interpretation. The interpretations identify influential input variables and summarize triggering patterns of actions. The second is decision explanation, which explain for an action taken at a state. This is an example of a specific policy illustration. In the Pong environment, a symbolic policy is first learned using reinforcement learning. The policy is then sent to the prompt template. GPT-4 receives these inputs and outputs the interpretation of the strategy. The first is Noop, which is mainly affected by the enemy's paddle in the first frame and the agent's paddle in the fourth frame. The lower the agent's paddle is, the higher the probability of Noop. Similarly, the probability of an upward action decreases as the agent moves upward. Finally, the probability of the downward action increases as the agent moves upward. LLM also explains the reasons for the decision for a specific state action. Here, the agent made an upward movement at the bottom of the picture. The first reason is that the ball is above, so go and hit the ball. The second reason is that the enemy also has to hit the ball upwards, so the agent moves upwards to deal with the enemy's position. The third reason is that the agent is at the bottom, so it needs to move up to hit the ball. Insight achieved the highest average return among 9 Atari games. Through end-to-end learning, Insight successfully optimized the tracking of object coordinates, making policy-related objects more accurate. By using a simple 3-layer CNN and lightweight symbolic reasoning, Insight achieves millisecond-level inference speed, which is competitive with neural baselines. Next, we are ready to take away our Insight method, which enhances object recognition accuracy and improves performance through end-to-end neuro-symbolic RL, and enables people without domain knowledge to understand symbolic policies through LLM-assisted policy explanation. Insight achieves the highest average performance and millisecond inference speed on 9 Atari games. You can do further research by visiting our website.